Welcome to this recording on geometric sequences for Unit 1, Chapter 1 of Mathematics 2200. We're going to define a geometric sequence, graph one, and find the formula for the general term. Now, sequences with a constant ratio between successive terms are geometric. So in this first example, 6 divided by 2, that's equal to 3. 18 divided by 6 is equal to 3. 54 rather divided by 18 is equal to 3. And 162 divided by 54 is equal to 3. Therefore, we have a constant ratio of 3 and we have a geometric sequence. We can also see that to get from one term to the next, we have to multiply by 3. For the next one, when I divide each term by its previous term, I get the same ratio. They're all equal to negative a half. That's our constant ratio, therefore it's geometric. For this third one, there's no common ratio, therefore it's not geometric. In this final one, each tower is half as high as the previous one, therefore we have a common ratio of 1/2 and it's geometric. An interesting side note here is that if we connect the corners of the tops of the towers like so, we get a nice curved graph. That tells us something about the shape of the graph of a geometric sequence. In this diagram we have tower number 1, 2, 3, 4 and the number of squares in each tower. So to help us draw the graph, I'll set up a table of values, tower number in this row and number of squares in this one. So we've got 1, 2, 3, 4, and we could continue the pattern. And next is the number of squares. So it's 1 in the first tower, 2 in the second, 4 in the third, 8 in the fourth. Our horizontal axis is our n values or tower numbers. So I'll just let that go by 1. So I'll just mark off every 5. Now our vertical axis will be our number of squares, our t sub n values. I'll go up by 2's. Plotting those points, 1, 1 would be here, 2, 2 here, 3, 4 right here, and then 4, 8 right here. And let's put in the fifth one. Notice how those points form a nice curved pattern, similar to the shape we'd get if we actually connected the top right corner of each tower. So you'll notice that our graph is discrete. In other words, we do not connect those points, and it's curved. Next, we develop a formula for the general term. Let's suppose I start with the first term of a geometric sequence. To get from that one to the next one, I first have to multiply that one by whatever the r value is. Then I take that term and multiply by another r value. So far I've multiplied term 1 by r and then by another r to get r squared. Then I multiply by another r value. So by the time I get out to this fourth term, I've actually multiplied term 1 by r cubed, and so on up the line. You'll notice that when we get out to, say, term 6 here, the value of the exponent is 1 less than the value of the subscript. Therefore, by the time we get out to the nth term, t sub n, that's equal to term 1 times r to the n minus 1. For example, in this example right here, the common ratio is 3. So the first term gets multiplied by 1 common ratio to get to the second term. Then it gets multiplied, we can take the first term multiplied by 2 common ratios to get the third term, etc., etc., etc. All this suggests the general formula for any geometric sequence may be written as the nth term is equal to the first term times r to the n minus 1. That n minus 1 represents 1 less than the subscript. And don't forget our domain is natural numbers. We can use this general formula to do several things. First, find a specific term in a sequence, and second, given a sequence, determine the number of terms. For example, in this sequence, which we've already seen, we know that the r value is equal to 3. We've got to find a formula for the general term. We use that general formula that we developed a moment ago. And therefore, for this sequence, the nth term is equal to the first term, which is 2, times our value is 3, exponent n minus 1. That's it. That's all there is to it. Next, we use the formula to find the 8th term. So t sub 8 is equal to 2 times 3 exponent 8 minus 1, which gives us 2 times 3 exponent 7. Follow order of operations and do the exponent part first. So we have 2 times 2187, which is 4,374. Next, we have to find the number of terms in the sequence. Well, really, that's the same as finding the position of 118,098 in the sequence. So we need to find the value of n. So we begin with our formula. We know that the nth term is 118,098. Our first term is 2. Our common ratio or constant ratio is 3. And we're looking for the value of n. But look where n is. It's up in that exponent. A common mistake here is to multiply the 2 by the 3 to get 6. That's going to cause you some issues. Another one is just to divide both sides by 2 and 3. That's another problem because you got this exponent here. What we actually do is divide both sides by this term 1 to get 59,049 equals 3 exponent n minus 1. And at this stage, because you don't have more experience with exponents, we'll guess and check that 3 exponent 10 is the same as 59,049. So we have 3 exponent 10 gives you 3 to the n minus 1. So what number subtract 1 gives us 10? That's going to be 11. In a nutshell, we can just cross off those bases. 10 equals n minus 1. So we have 11 terms. Key idea is a geometric sequence has a constant ratio. The graph is curved and discrete, has domain natural numbers, and the formula for the general term is t sub n equals t1, term 1 times our exponent n minus 1.